The device at right allows you to ski uphill until you smash into the pulley. The ballast block has a mass of 60 kilograms, and the skier has a mass of 70 kilograms. The coefficient of friction is 0.1 for static, 0.09 for kinetic. The ramp is inclined at 20 degrees above horizontal, and the pulley is 45 meters away. So we're going to use the work-energy relationship to solve this problem. The work-energy relationship says KE1 plus GE1 plus work 1 to other is equal to KE2 plus GE2, or you can write this as 1/2 mv1 squared plus mgh1 plus sum of forces times displacement times cosine of angle between the two is equal to 1/2 mv2 squared plus mgh2. We have to fill out a table for the skier and also for the block. And so we're going to do a free body diagram for the skier and also for the block. For the skier, I'm going to say the skier is going in the positive x direction and y is perpendicular to the incline, which means that for the pulley, the positive x direction is downward because the pulley redirects the coordinate system. So, for the skier, I have the force of the rope, let's call that T, acting up the incline. For the block, the force of the rope is acting upward. I have a force of gravity acting downward. This is equal to the mass of the block times little g. The mass of the block is 60, so that's 60 times 9.8, which is 588 newtons. Then for the skier, I have a force of gravity acting straight downward. That's equal to the mass of the skier times little g. The mass of the skier is 70, so this is 70 times 9.8, which is 686 newtons. I have a normal force, which is perpendicular to the surface of contact, and I have a force of friction going down the incline, and because it says the skier is going to ski uphill, this is kinetic friction because the skier is moving. The skier and the block start from rest, so kinetic energy is 0 for the skier and 0 for the block, and let's set the reference point for gravitational potential energy to be the initial height of the skier and the initial height of the block. And then let's look at final gravitational potential energy. So remember, gravitational potential energy is m times g times h. When the skier goes 45 meters uphill, 45 meters of rope is going to go over the pulley, so the block ends up 45 meters below where it started from. So gravitational potential energy for the block is m times g times negative 45, and m times g is 588. So this is 588 times negative 45, and that gives me negative 26,460 joules. It's negative because I said it started at 0 and it goes downwards. For the kinetic energy of the block, I don't know what it is, but I do know it's 1/2 the mass times the final velocity squared. So the mass is 60, 1/2 the mass is 30, and this is v2 squared. Similarly, for the skier, it's half the mass, which is 35 times v2 squared. Since the skier and the block are connected by a rope, their final speed is the same. For the skier, gravitational potential energy is m times g times h. The skier goes 45 meters up the incline. The angle is 20 degrees. So this is H2, and that's equal to 45 meters times sine of 20 degrees. So gravitation, and that 45 meters times sine of 20 degrees is 15.4. So if the height is initially 0, H2 is 15.4. Gravitational potential energy is m times g times h. For the skier, m times g is 686. So this is 686 times 15.4, and that is equal to 10,564. Now I need to worry about the work. For the block, the displacement is downward, the tension is upward. This is the displacement for the block. So I have the force times the displacement times the cosine of the angle between the two. Cosine of the angle between tension and the displacement is 180, so that gives me a negative sign. So the work done by tension is minus T, the displacement is 45. And this is work done by forces other than gravity, so that is it for the block. For the skier, the displacement is parallel to the incline. The normal force is perpendicular to the incline, so the angle between the normal force and the displacement is 90 degrees. So the work done by the normal force is 0. I do not include the force of gravity when I calculate the work done by forces other than gravity. I have tension acting in the same direction as the displacement, so that's cosine of 0 degrees, which is 1. So that's T times 45 times 1. Then I have the force of kinetic friction going down the incline, so that angle is 180 degrees, so that's minus 1. So that's minus force of kinetic friction times 45. Now we're going to do the work-energy relation for the skier and for the block. So I have KE1 for the skier is 0 plus GE1 is 0 plus work done by forces other than gravity for the skier. Let's pull out the 45. No, it doesn't matter. We leave it in. Minus force of kinetic friction. I have to figure out what that is equal to 35 times V2 squared plus 10,564. Okay, I'm going to come back to the skier in a minute, but I want to write out the work-energy relation for the block first. So for the block, we have 0 plus 0 minus T times 45 is equal to 30 V2 squared minus 26,460. So it's this plus this plus this equals this plus this. Okay, now I have to figure out what the force of kinetic friction is for the skier. If I was looking at impulse momentum in this problem, I could figure out the normal force that way. But I'm not looking at impulse momentum, so instead I'm going to apply Newton's second law in the y direction to figure out the normal force. For that, I have to break the force of gravity down into components. This angle is 20 degrees, so this angle is 20 degrees. You can take a moment to convince yourself that that is true if necessary. So this is the cosine component, so this is 686 times cosine of 20 degrees. And when I sum up the forces in the y direction for the skier, the only forces I have going in the y direction are the normal force and the y component for the force of gravity. So I get, for that, the sum of the forces in the y direction is equal to 0. Therefore, the normal force is equal to mg cosine of 20 degrees, and that is 645. And then the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. The coefficient of kinetic friction is 0.09. So for the force of kinetic friction, I have 0.09 times 645. That gives me 58 Newton. So I'm going to take another line to rewrite this. This is minus 58 times 45. Let's actually figure out what that is. So 58 times 45 gives me 2,610. That's equal to 35 times V2 squared plus 10,564. So now I have two equations, two unknowns, and if possible, I like to solve my two equations, two unknowns, by adding them together, which will work very nicely here. If I add 1 and 2 together, I have t times 45 here, I have negative t times 45 here, so that will give me 0 when I add those together. And then I have my minus 2,610 here, which is equal to 35 plus 30 times V2 squared, so that gives me 65 times V2 squared plus 10,564 minus 26,460. And then I can say minus 2,610 is equal to 65 times V2 squared. 10,564 minus 26,460 gives me negative 15,896. Then I can add that to both sides. That gives me 13,286. Then if I divide by 65 and take the square root, that gives me V2, and that is 14.3 meters per second. So that's the final speed for the skier and for the block. And I can also go back to either equation 1 or equation 2 to find the tension. Let's use equation 2. And I have, while we are here, let's divide both sides by negative 45, and then we'll have t is equal to 30 times V2 squared minus 26,460 divided by negative 45. And that gives me 452 newtons. So I found all the unknowns in my work-energy relationship, and so now I know all the unknown forces, I know the masses, and I know the final speed.